Now, I'd like to talk about the geology of Tenerife and also about Teide National Park. And it's been a place where I've been working since my PhD. And I was doing my PhD on the neighboring island of Gran Canaria. And Tenerife is, of course, the crown, the jewel in the crown of the Canary Islands. And I started just after my PhD working on Tenerife. And yeah, so I'd like to share some of the experiences I have with you and some of my understanding. I'm not claiming that I know everything, but let's see how far we get and how many of your questions I can actually answer. So here we have a little summary, a little content list of the things I'd like to discuss with you. And here I'd like to kind of go into the age and evolution of the Canary Islands, first of all, a kind of more general overview. And then I'd like to talk a little bit about the different stages of Tenerife, the evolutionary stages. We will then focus a little more on rift zones and also landslides, giant landslides in particular. Then I will also mention the shield basalt complexes, in particular Teno and Anaga. And then we will spend a little bit of time on the Las Cañadas volcano, the big volcano that was there prior to the current Teide and Pico Viejo complex. The Teide and Pico Viejo complex is relatively young. It's only about 200,000 years old. That's when it started. And we will kind of discuss this in some detail because this links to the currently active rift zones, and it also links to the historical eruptions, and it's the centerpiece of the Teide National Park right now, which is one of the most popular national parks in Europe, and actually the most highly visited one in Spain. So it's a real kind of tourist magnet, and it's therefore economically as well as culturally very important. So where are we going? We're going to the northwestern coast of Africa, and here's a group of islands, the Canary Islands. There's a few other islands around, and we have the Madeira archipelago a bit further south, the Cape Verdes, but the Canaries are very prominent, and they're very popular, as I said, for tourism. So I'll mention this aspect a few times. And Tenerife is the central island of the archipelago. The archipelago has 7 islands, and Tenerife is one of the largest here. And Tenerife is also the tallest of the islands, and this is why the Pico of Tenerife, Teide, has been a navigational landmark for many, many centuries. And here is a Dutch drawing from several hundred years ago. And of course, the mountain is oversteepened, but this was a good reference point because the sailors could see it above the clouds from a far distance. And then visitors have been drawn to the island for many centuries, as I said, and there's a drawing here from the 1785 eruption and early tourist photo from the Orotava Valley with Teide volcano in the background. And I'll come back to these sites a little later. So the first scientific relevance of Tenerife was when people tried to determine the height of Teide volcano. This was going on for quite some time, and people believed that if you're on top of Teide, the sun will be so intense that you get burned. So it was very important to determine how tall Teide is, and this was eventually done by triangulation. But several estimates were out there in the literature. They were grossly different. And it was left to this gentleman here to confirm a previous estimate. And Humboldt, he visited Tenerife on his way to America. He was there for 1 week, and he climbed up to Teide. So he was quite pioneering, and he also determined the height of Teide, and he got it right within a few meters, and he got pretty famous for that. So he visits Teide and several other places, La Laguna and the Orotava Valley, and I mentioned something about his visit to Orotava a little later in the lecture. So he was quite perceptive, and he realized that the island has many different plant species, and they are linking up with altitude. So he realized that down near the coast, it's very tropical, but high up on the mountain, it's almost Arctic. And he correlated the altitude with latitude. So he realized if you go higher, it's like going further north. And this is why you might have snow on Teide while you have sunshine and palm trees down at the coast. And he came up with this little drawing here where he shows the vegetation changes with altitude. And this was one of the kind of first geographical breakthroughs that Tenerife has helped to deliver. And he also, as I said, measured Teide's height, and he got it right within a few meters, and confirming a previous estimate by a French scientist. And because there was suddenly complementary data, people believed this, and indeed they were very close to the true value. So he was also arriving at Tenerife as a Neptunist, but he left as a Plutonist. He realized that lava comes from volcanoes, and he further confirmed this in his travels in America. So Tenerife was a game changer for Humboldt and therefore for science in general. Now, Tenerife is also a tourist spot, and we must accept that, and this is partly because of the nature. And this goes back to people like Agatha Christie. There's a statue of Agatha Christie in Tenerife, and tourism was pioneered in Tenerife. And it's, of course, going strong to the present day. Maybe not for the last year, but I'm confident it will come back after Corona is hopefully sorted soon. Now, another important thing is that already since the Spanish conquest, the lower altitudes were used for agriculture, and banana production is very big in the Canary Islands. It's got a downside. It takes up a lot of water, unfortunately. So there's increasing water problems on the Canary Islands. But in terms of agriculture, tomatoes and bananas and pineapples, things like that, a lot of them that we consume in the European Union actually come from the Canary Islands. Now, this is in Orotava, one of the fancy places, and it reminds me of Agatha Christie novels. Probably there is some detective there looking for some bad things that happened there in the fancy hotel. But yeah, it's been a travel hotspot for many, many decades, and it will likely continue to be so for many decades to come. So, but today we shall focus a little more on the geology, and here is a map of the Canary Islands. And as I said, Tenerife is a centerpiece, and Tenerife is an isolated island, but there is a channel between Gomera and Tenerife. So Gomera has no historical eruptions, but there is a shallow channel in between. So some people argue Gomera is somehow connected. And a bit similar, Lanzarote and Fuerteventura have only a shallow channel in between. So geologically, you could actually argue there is a link, but in terms of eruptive centers, Gomera has its own central volcanic system. So it's more like that there's two large volcanic systems that have partly grown together. If both islands would continue to erupt at high rates, they would likely form one larger landmass. But we are not sure whether this will happen or not. This is something that only the future will tell to future geologists, I'm afraid. So the islands are dominantly separate entities, apart from, as I said, the connections between Lanzarote, Fuerteventura, and Tenerife and Gomera. And they are on a pronounced ridge. It's also geophysically determined. It's a gravity high. And here's just some impressions. And the most recent volcanoes, the youngest volcanoes, El Hierro and La Palma, they are growing at the most westerly end of the island chain, and they're also amongst the smaller islands. So one gets the impression of older, more mature islands being in the east and younger, evolving islands being in the west, which led to the concept of an age progression amongst the islands. And indeed, this has been a vigorous debate for at least the last 40, 50 years. And the oldest eruptive rocks that have been determined on the islands seem to young towards the west. On Fuerteventura, the oldest rocks are 20 million years, while on El Hierro, the oldest erupted rocks are only 1.1 million years. This has led to a plume hypothesis, like for the Hawaiian Islands, where we have the plate progressing, but the Atlantic plate only moves with about 2.5 centimeters a year, while the Pacific plate moves a lot more rapidly at something like 7 centimeters. And the alternative view is that the Atlas Mountains might actually connect to the Canary Islands. There could be a fracture connecting to that. And this has been a vigorous debate, as I said. I personally believe the Plume hypothesis is closer to the truth, and I will give you the evidence for that I think applies. But of course, I mean, the debate will likely continue for some time. But first of all, one of the key evidences is the Atlas fault does actually not continue submarine. It's never been found to continue offshore. And it just happens that the islands lie along a projection of that. Another issue is that the Madeira archipelago shows the same curvature as the Canary Islands archipelago, and therefore there is no Atlas fault that connects potentially to Madeira. So something else seems to go on that is much, much bigger in a geodynamic scale. So, and of course, as I said, the youngest islands are furthest to the west, which in a fracture situation should not be the case. In a fracture situation, you get random age distribution along the fractures like you get in the Cameroon volcanic line and also in the Azores. This is not the case in the Canaries. And also the erosion pattern seems to fit. The old islands like Lanzarote, Fuerteventura, and Gran Canaria, they're more deeply eroded. They're less tall, while the young islands and the central island Tenerife, which is believed to be at the peak of growth, and La Palma, for example, being a juvenile island, they are quite pointy and steep with frequent eruptions. And this would also confirm an age progression. Moreover, the sedimentary debris fans that come off the island seem to overlap in a way that the younger ones to the west seem to onlap onto the older ones to the east. And also, if you look at xenoliths that have come up in the islands, the xenolith from sedimentary rocks under the island seem to be the youngest in El Hierro, which is only 1.1 million years in terms of eruptive age, while on Fuerteventura you get uplifted Cretaceous rocks in the center of the island. So the sedimentary strata under the island seems to be also younging towards the west. And to discuss this fracture and plume hypothesis a little more, as I mentioned, the Madeira archipelago seems to have a similar curvature. And I discussed this in a little paper already in 2015, and just in the next few days, apparently, maybe there's a delay, but Juan Carlos Carracedo and myself have a new paper coming out in the Encyclopedia of Geology, where we discuss this in more details about these islands, and these figures are from that paper. Here we did a little calculation, and you can actually calculate an Euler pole, a rotational pole that's somewhere off in the Atlantic, and that would allow to actually have both island groups, Madeira as well as the Canary Islands, to rotate around this Euler pole. And this is consistent with the rotation of Africa bumping into Europe. Another aspect is that if you look at earthquakes, there's a lot of earthquakes along the mid-ocean ridges and along the Azores that sit on these triple junctions. And there's very few earthquakes in the Canaries, apart from some associated with small-scale volcanism. And the earthquakes in the Atlas Mountains, they don't continue down into the Canary Islands. So this fracture system is not confirmed by earthquakes either. So there's a good case to be made that a plume is the more likely scenario. And not enough, the magnetic anomalies from the ocean floor, there's M25 and S1, it's 175 and 156 million years. They are actually at an angle to the islands. So the islands go across the ocean floor fracturing, and this is kind of inconsistent with the fracture model to a large degree, I would argue. So here's just to emphasize this point, the Azores, they sit along fractures that are transform faults and oceanic fractures from the mid-ocean ridge. And the islands are very elongate. All the vents, that's the dark dots here, all the vents are along the fracture outlines, while in the Canaries, the vents are distributed more randomly. And we'll talk about triple junction rifts in a few minutes, but they seem to not strictly correlate with ocean fractures at all. And as I said, the orientation of the archipelago actually goes at an angle relative to the magnetic anomalies. Last but not least, there has been geophysical evidence coming up over the last 20 years. And here we have some seismic tomography from a science paper by Montelli and others. And here they believe they can see their source, the Canary Islands and the Cape Verde Island anomalies going down to the lower mantle. And if that's correct, then it's not a fracture problem that is close to the surface, then it's a deep plume scenario. And here's more of their work. And there has been several other studies now seemingly confirming this, but these anomalies, they can be traced down to the core mantle boundaries, at least according to these data. And that would be a very strong indication for the plume hypotheses applying to the Canary Islands more strongly than a surface fracture model. So this brings us to this kind of scenario, and this is one of Juan Carlos Caraceiros' slides. So some of the slides are in Spanish, but you get the idea. So I think we are dealing with a plume that is underneath a slow-moving plate. This is why the islands are not quite so spread out as Hawaii, but there's an age progression, there's an erosional pattern, there's an age progression with the underlying sediments, and the geophysics is aligned with that as well. The earthquake patterns would be consistent with the plume origin rather than a fracture origin. So I think the plume model is most convincing, at least from my perspective. So, but now let's talk a bit more about Tenerife, having covered the archipelago and the origin of the archipelago. Tenerife is the jewel in the crown, as I said, and this is because it's the island that has the most advanced evolutionary stage, but is not eroded yet. And that makes it kind of an amalgamation of all the processes we see before it's taken down again, making it a superb example. And it's large, it's comparatively large, larger than the other islands. And it's also got very high elevation, over 3,700 meters. And it's got over 900,000 people living on it. And it's got a very high population density, 444, according to the 2019 data. You might or might not know Sweden's population density is 24 per square kilometer. So there's a lot of people living on the island for good reason, because it's a fantastic place in terms of climate and landscape and also agriculture. So here's some highlights of the islands. I mean, there's the old shields in panel A there. This is Los Gigantes from the Teno shield. Then we have the Las Cañadas volcano with the big ignimbrites. We have the Las Cañadas caldera on top of the island, and inside the caldera, the young volcano Teide and Pico Viejo is visible. And from there, we have the rift zones going out. And in the distance, you can see the other islands here, like La Palma and La Gomera. So this is some of the highlights. And we have a very good eruption record there from prehistorical eruptions. And prehistorical in the Canaries means prior to the Spanish conquest, which effectively is the 1490s. And then we have some historical eruptions as well. The eruptions in historically recorded time have all been rather harmless and small, so there has been no big explosions. The last major explosive eruption is about 2,000 years ago. And therefore, there is a good chance that most eruptions in the future, at least on our life, in our kind of lifetime, will likely be very small and nice to watch. So hopefully that will be the case. Tenerife has these three arms, and all of the historical eruptions happened to be along these rift zones. And in the little map in the top right, there is in black, the historical eruptions, 1704, 1705, 1706. There was a few kind of eruptions in quick succession. Then there was one in 1798, and then in 1909. And when Columbus passed the island on his way to America, he actually spotted an eruption on the rift zone, and it has been found by now by radiocarbon dating. They were able to pin it down to the right age, and that is the Boca Cangrejo eruption, as it's called, and that is 1492, which is nowadays believed to be the first historical eruption because there is a record. Columbus reports that his sailors were really nervous about this, but he came from Italy, and he said, oh, it's just nothing special. Etna does this all the time. And so he calmed his people down, and but there's a good entry in the logbook, but he pointed out that it's in the Sierra of Tenerife, not on the peak. And this is what helped to identify the eruption, and I'll show some images of that later on. So it was a rift zone eruption as well. So this is Teide, and Teide had a summit eruption in medieval times, not in historical times, but it's not erupting from the summit any longer, it seems, and we'll talk about that a little later as well. Many of the eruptions now come from the periphery, and the simple argument is that Teide may have grown too tall. It might be easier for the magma to come out at the sides than going all the way up, but more on that a little later. So now the rift zones, and here's an image from the southern end of the island, and in the little map in the top left, you see a little red box. This is from the very south, close to the airport, and here we have alignments of vents of sintercones, and they're quite beautiful. And at the very southern end, some of the lava from the sintercones has entered the sea. There's some pillow lavas there as well. And this is what we get down in the south. That's the expression of the southern rift zone, but this is the weakest of the rift zones. And I will try to convince you later that this is a passive rift zone, while the other two rift zones are more active. But let's wait until I have a chance to give you the evidence for that. So the big rift zone is the northeast rift zone, or the Cumbre Dorsal, as it's known on Tenerife. And here we have it viewed from Teide volcano, and here it's above the clouds. There is this sea of clouds that already Humboldt described, and it comes in at an elevation of between 1,000 and 2,000 meters. And here you see just the above the cloud expression of it. And it's tens of kilometers long. It's relatively narrow in the highest part of it, and it's clustered with vents close to the central complex. Further away, there's still vents, but there's also quite some severe erosion, which allows us to look into the rift zone. Quite a magnificent opportunity for geologists. Here's just a Google image, and this is vertically exaggerated, just to give you a flavor. And the interesting thing is there's a forest corona, and you can see that here in green, in a slightly darker green. There's this rim of trees around it, and while there's very little rainfall in most parts of the island, there's a lot of clouds, and these trees have managed to kind of live off the dew that's condensating and then dripping down to the ground. So they are catching the clouds, if you will, and that makes for this rim at this altitude where the clouds are. Very fascinating in terms of botanical things. And yeah, Humboldt was one of the first to see that this is kind of what's happening there. And the rift zone itself, once we see a little bit of surface erosion, we can look inside the rift zone, and there is a lot of dikes. So rift zones are effectively dikes into dikes, and they feed sintercones at the surface. And here is one of the prominent dikes just at the margin of the national park on the right-hand side. And just a little bit further down along the northeast rift zone, you see this kind of set of dikes on the left-hand image. And here there's quite a high density of dikes. And this is how the rift zone looks inside. Here's a few more impressions of the same thing. And I had 2 PhD students on these dikes some years back, and Audrey Del Camp and Francis Deegan, and one was doing the structural aspects, the other one the geochemical aspects. So we numbered all these dikes and we drilled all these dikes, and although we had permission, people complained afterwards that all the dikes are ugly now with the drill holes, so we had to fill many of the drill holes again, but we have a good record of them now. So, and most of the dikes have no holes anymore, at least not those in the national park. So it was a bit weird. I think the Spanish people were not quite clear about what they're getting into when they gave us permission. But anyway, as I said, it's fixed now. And what we also did at the time, it's not possible any longer, but at the time it was still possible to go into some of these water tunnels, the galerías. Because of the water shortage on the island, there has been thousands, literally thousands of water tunnels drilled into the mountain to get water out. Tourists consume huge amounts of water, so the internal water table is dropping constantly because of tourism largely. all the swimming pools and things like that. And therefore, it's necessary to create extra water sources. And you can go into these, or at least you could. But then there was a big accident in 2007. 6 people died in them because of asphyxiation. So they died of gas, and they were just going in there. They weren't prepared. So you see the little pipe there in the right-hand image. And usually, if you want to go in there, you had to ask for permission, and then they would pump air in for 2 days or 3 days before you go in. And these other people didn't ask for permission. They just went in, and this was not so good for them. So here's some impressions from inside the rift zone. And there's a lot of dikes in there as well. And some of them are quite water rich. This is what they are mined for, water. And some of them have little railways. You can go in for quite a while. And the longest is several kilometers long. But the rock composition is dominantly basaltic or basanitic, a slightly alkaline variety of basalt. And there is some very rare, more evolved compositions, as you see in the total alkali silica diagram in the top right. And the dominant rock type is basanite, and then there's some tephrites. So the rift zones are effectively basaltic in the widest sense. And this is a very important takeaway point here. And this is from the PhD thesis of Francis Deegan. And here we see that, I don't want to go into details, but here we see the fractionation trends. And there is a little bit of assimilation of country rock, but not very much. And it's very strongly indicative of fractionation processes at deep level, probably below the island. And also the isotopes suggest that much of the northeast rift zone come from the central volcanic edifice. We'll talk a little bit more about this later. And this is a nice alkaline fractionation series. And there's nice rocks like ancamerites and picrites, olivine-rich ones like the picture in the very bottom in the center. And then pyroxene-rich ancamerites, which is the pictures in the center top. And then we have some feldspar-furic ones, the most evolved ones. That's the little picture in the top right-hand side. So this is what we're expecting inside the rift zone. So you can actually go inside the volcano. It's getting a little warm and wet in there, but this was a great experience as long as we were able to do that. And this is what we found in there. So, and here you now can see the rift zone at the surface. This is Teide volcano in the center of the island. And here we see some sinter cones in the foreground. This is what the surface expression of the northeast rift zone looks like when it's not eroded. So it's an alignment of vents, many monogenetic vents, quick successive eruptions, I would think. And the rift has been active for well over 1 million years, according to the dike dating we did. And it's also where some of the recent eruption happened. So it's still active in this context. So here's a close-up of Teide, and you'll see the rock colors around Teide are a little different. That's phonolites, and we'll talk about them in the second part. But in the foreground, you see these mafic vents, these basanitic and tephritic vents. And you'll note very quickly that they seem to have an opening to one side only. They're all horseshoe-shaped. And it's intriguing. I was very puzzled by this until Juan Carlos Caracero told me, oh, it's very simple. They're all in the same orientation because that's the wind direction that determines that. So when the wind blows from the Atlantic inwards, then you get less deposition on one side than on the other. And that's why they all look the same or all very similar, because the wind always blows from a similar direction. So what a wonderful explanation, I thought. So, and here now the rift concept. Initially it was, oops, let's see. The rift concept is that initially it was thought that the plume pushes the plate upwards and it makes these cracks, these triple-armed cracks, and this would allow triple-armed development. I was always a bit skeptical because we would then expect that all the islands have 3 arms, and that's not quite true. And by now, we know from analog experiments, if you have an extent, an intruding extent, i.e. a surface that pushes upwards, you actually get radial cracks, not triple-armed cracks. So it's a bit more complicated, and it caused me to investigate this a little more. But Here is the simple observation. The center is a big stratovolcano, Pico, Teide, and Viejo, and it's dominantly phonolitic, while the rift zones are dominantly basaltic, and they have been going strong for quite some time. So it demands an explanation why these triple arm systems are evolving. And here, the least effort branching principle was published by Carcedo in 1994. But this is one of the concepts where I'm not in full agreement with Juan Carlos Carcedo. I have a slightly different idea about this, and we discuss it in the 2013 Teide book, where we both give our ideas in the same chapter, and then we discuss it a little, but I think we're reaching a consensus, and that is that most of the rift zones seem to occur in volcanoes that are pretty big. They don't seem to be there in very small volcanoes. So the size of the edifice has something to do with it. And what we believe is that once the island grows to a certain size, then we're starting to develop instabilities. And dikes may cluster around these instabilities, and you get landslides in between dike swarms. And this is the kind of idea. So there may be fractures that play a role right from the start, but the island itself, the growth of the island, also plays a role. And here, I'd like to now start moving towards the basaltic shields at the ends of the island. What we found is that not only has Tenerife 3 arms, actually some of the old shield volcanoes have also 3 arms, like the Anaga shield and the Teno shield. And if these guys, these little volcanoes or these little shields have their own systems, then it's obvious it's not ocean floor fractures. It is actually something that the edifice develops when it grows to a certain size. And although rift zones were first defined on Hawaii, actually they're much better developed in the Canary Islands, as you see on the right-hand image, with there's a vent density map. And the vents on the Hawaiian Islands, they form a triple-armed rift system, but it's less well-defined than on El Hierro or on Tenerife, where you have these really strong examples. So let's move to Anaga for a short while. We're going to the old shield. Anaga was one of the shield volcanoes that then eventually was incorporated into the island of Tenerife. So likely there were several little volcanoes popping up around, a bit like Surtsey in front of Iceland, but eventually if Iceland grows, it will be swallowing up Surtsey. And this is, I guess, what happened here. So here we have a view towards Teide from Anaga. And this is the entire northeast rift zone in all its length. And here's the Anaga shield volcano. It's a little older. It's over 5 million years old. And it had a major landslide, so this works well. And it has a lot of dikes and some old rift zones. And we studied those, and what we found was that the dikes seemed to come up in pulses or in generations. First of all, there was a linear rift, and then there was a curvature of the rift, and that coincided with a landslide. And after the landslide, we had 3 arms. So we started to think, oh, I see, there is some indication that the landslide might actually create the 3rd arm, that there's a link between landslides and rifts, and that would make sense with the concept that big volcanoes develop rifts. So we dated the landslide in a paper in 2005, and the landslide occurred around about 4.2 million years ago. And we see some rocks that are older underneath the landslide from the exposed surface. And here is our little conceptual sketch. It was published in Walter et al. 2005 in Bulletin Volcanology. And here we believe we can determine that the dikes respond to the landslide. They can sense the landslide. Well, of course, the dikes don't sense anything in reality. It's the fractures that form. And the fractures would then allow dikes to take different shapes and orientations. So our model there is that ridges will eventually develop triple-armed segments once we have landslides and instability. And here's a little numerical model from that work. And this is where we have a 3rd passive arm, a relaxation arm, forming as a consequence of the landslide. So if you slide a big chunk of the volcano down, you relax the other side of the volcano. And if that happens, you get fractures there. And this would explain the development of this weaker third arm. And that's also what I believe to apply to Tenerife as a whole. The southern rift zone is the weaker one, the more passive one, while the northeast and northwest rift zones are a lot more active. And I think that's the active rifts, if you like. So a quick excursion into some analog model. And yes, we're good for time. So this was so intriguing that we started to do some jelly volcanoes. And if you take a jelly volcano and you just put it on the surface, it sacks a little in itself. But if you inject little liquid dikes, just colored water at the time, you get these radial patterns. And it's a real pain to make triple-armed rift system. Basically, we failed to make triple-armed rift system unless we create an unstable sector. The unstable sector here was just an area where we put a lot of washing up liquid in there to lubricate the surface. And that created the jelly volcano to sack to one side. So it had some internal strain simulating instability from an impeding landslide. And once we do that, whoa, we actually can make triple-armed rift system when we inject right in the zone of instability. So stable, nice volcanic edifices, they make radial patterns, while if you have these instability systems of one sector, that's the time to make triple-armed rift systems. And so I'm quite convinced that the triple-armed systems are quite frequently caused by volcano instability. Some of them may originate from fractures in the ocean crust, no doubt, but the volcano can change its shape according to its instability history. That's at least the model I would propose. So, and here, this, I just mentioned it, this is why I believe the southern, the weakest rift zone is actually the passive arm. So I think this little study from Anaga translates reasonably well to the island as a whole. And here, the most volcanic activity is happening on the big, strong northeast and northwest rift zones. And therefore, I think if the island grows in the future, it will grow to the north, northeast, and northwest, and not quite so much to the south. So, but this leads me on to some landslide discussion. I mean, this has been in the media quite big and goes back to several studies from some 20 years ago. Well, it's undisputable. There is big, giant landslide scars in the Canary Islands. There are thousands of cubic kilometers in terms of volume, and they have large run-out distances, hundreds of kilometers. And virtually all the Canary Islands have them documented, apart from La Gomera, but that may well be just a function of the age of La Gomera, so we don't see it because it might be covered with other deposits. So all the other islands have evidence for large landslides. They are very rare on human timescales, praise the Lord, but they are geologically not unfrequent. And there's something like 100 events of this magnitude worldwide that we have recorded. And the 2018 collapse of Krakatau is a vivid reminder of these things happening. And like with Krakatau, we get tsunami as a result of that. So if something like this happens today, we would have to think about huge geological hazards coming from tsunami waves. So here is the Guima landslide on the eastern side of the northeast rift zone, and behind it is the Orotava landslide. So there's landslides on both sides of the rift zone, and these were creating instabilities. And actually, you can just about see a slightly darker lava delta in the middle of the image. This is the 1705 eruption that were actually happening along the rift zone, where it was starting to partly fill the Guima landslide. And there's a big tsunami deposit on Gran Canaria opposing this Guima landslide, which also dates from that time. So there's good evidence that a big tsunami hit the other island with run-up altitudes of up to 200 meters. So the wave was running up the coastline for quite a bit. So if that would happen today, all these coastal villages on the neighboring islands would be severely affected. So here's the concept here. Tenerife has several large islands, and in fact, even Teide is actually growing in an old landslide scar, the Icod landslide that happened at about 200,000 years ago. And one of the video clips that I sent had some tsunami deposit. That's the one from the Ecot landslide. At least that's what researchers believe. And the good thing about these landslides is that biologists believe that they have helped to colonize the islands. The idea is that rafts of vegetation might be floating from island to island, and this is how you get vegetation even to the Azores. So for biology, there is some advantages with these last landslides, but if you would happen to be in a little boat just in front of it, I think it wouldn't look good for you. So here's the Orotava landslide now, and it's this big depression in front of Teide volcano. The Orotava landslide is about 560,000 years old, and it was also one of the landslides on the northeast rift zone. So this link between rifts and landslides is quite strong, quite pronounced. And I mentioned earlier that Mr. Humboldt was visiting this place, and he was really fond of the Orotava Valley, and he has a little memorial there in the Orotava Valley. So here you see this bronze statue of Mr. Humboldt admiring the Orotava Valley, and the Orotava head scar is just visible in the distance, and the Teide, the young volcano, crowning the scenery here. And he loved it so much, he actually expressed in his diary that he was touched to tears and that he would love to settle there. He never came back to the island, unfortunately, but he was really fond of it at the time. And he described 3 sinter cones inside the Orotava Valley. So there were 3 little younger volcanoes growing. Today, we only have 1.5 left. They have been quarried for the lapilli. They use the lapilli for agriculture and for building supplements. And unfortunately, only 1.5 of these Humboldt cones are left today. They're now protected, but back in the last few centuries, they were not. And one of them has a hotel on top of it. It's this red building in the bottom right-hand image. And it's a very exclusive hotel. I've never been there apart from kind of having a quick look at the foyer. The other one has a lovely restaurant, and I've been to the restaurant. That's very nice. So, but the third one is completely gone, completely mined away. So, but as I said, these landslides, they have caused big media attention. And here is a model, a geophysical model for a potential collapse on the island of La Palma. And if this happens, then it's believed that we get a big tsunami wave, and this might even hit the east coast of the US and reach Florida. And that, if true, would cause a lot of devastation. And this was big in the media when I was a PhD student, and it's been recently resurfacing as an argument. The good news is this flank on La Palma, it's been monitored now for well over 20 years, and it has not moved a single millimeter. So I think we're pretty good, but of course, geologically speaking, this is a reality. These phenomena do occur, and if they occur, they will be serious, but their frequency is very, very low. So by all measure, we will not experience a thing like that in our lifetime, and probably not in many human lifetimes to come. But we cannot exclude that it will happen again at some point in the future. So then I would like to talk a little bit more about the old shields, and we've touched on Anaga, and now I'd like to take you to Teno. That's the old shield in the northwest, and this is now partly overgrown by the new volcano, by the new rift zone, but we can still go there and see some of the old features. So the basic concept is that there was 3 old shields that were growing and eventually merging together: the Teno shield, the Anaga shield, and what some people call the Roca del Conde shield, or I guess from my perspective, I would call it the central shield. And I like to think that the Las Cañadas volcano, the yellow one here, is just a continuation of the Roca del Conde, or the central shield. So effectively, it's 3 kind of volcanoes that have somehow merged, but one of them was stronger than the others, and that eventually overgrew the others. There has been no direct eruptions in Anaga and Teno for several million years, but of course there has been eruptions in the center of the island. So the central shield seems to be the most dominant one that is overgrowing the others. So to go and focus a little bit on Teno, Here in the far northwestern end, the old Teno shield is exposed, and it's got some spectacular landscape. Planet of the Apes was filmed there, by the way, just because it's such a magic landscape. And it's also a little shield volcano with landslides and rift zones. So it's a miniature version, an older miniature version of island development. And I had a PhD student there, Marc-Antoine Longpré. This is well over 10 years ago, but he mapped some of these rocks there and did a little bit of geochemistry there as well. And there has been 2 successive landslides, probably to the northeast. And there's a good rock record from these areas. And let's see, yeah. So here you see the landscape is spectacular because of the deep eroded canyons there. And there is several older seaward dipping layers of lava, and then there's a big debris avalanche deposit, and then that fills what we believe to be a collapse scar, and then this is followed by a second debris avalanche that cuts infilling lavas, and then we really must think about successive landslides, and the second one seems to be associated with quite a bit of explosive volcanism. So we think that there was a bit of big eruptions associated with the collapse of the second one. So if you put geology onto this one here, so the debris avalanche of the first collapse is the yellow rocks. They are cutting the eastward, the seaward dipping reflectors in red. And then we have the second debris avalanche, which is marked by these turquoise bluish colors. And then we have these youngest lavas from Teno that fill in the second collapse. So 2 successive collapses, but this was millions of years ago, so they're not very recent. But they are associated with the submarine debris avalanche, so they are quite real. And this gives us a sense of how these shields develop. So this is work by Marc-Antoine Longpré, as I said. And here we have this succession in a simplified way. We have a volcano growing, and then it's collapsing, it's regrowing, collapsing, and then regrowing. And intriguingly, it comes with these big explosive deposits after the second collapse. And we believe this, at least Marc-Antoine wanted to be, he was a French Canadian, he liked North American geology. So he always liked it, likened it to Mount St. Helens and the collapse from Mount St. Helens, which then caused a big explosion as well. So he liked to think that this was what happened there. And here's some of these deposits from the second debris avalanche, and some of them are clearly pyroclastic and with strung out glass. So there was probably quite some truth in his proposal that there was a big explosion or big explosions associated to certainly the second debris avalanche. Now, another intriguing feature there is that is the crystalline nature of some of the lavas. This is really beautiful. If you go there, you will see that there's beautiful thick lavas, partly columnar jointed, but they have huge crystal aggregates and crystals of pyroxene and sometimes olivine. And you can see what we believe to be crystal settling in some of the flows. They must have been super hot and gas rich, and they must have come from very deep. So likely associated with the landslides, some decompression phenomena allowing crystal-rich material to rise up very quickly. Otherwise, this might have not erupted, but due to the landslides removing maybe a kilometer of overburden, these things would have come up rather rapidly, bringing up very dense crystal aggregates from very deep. And you probably heard that Iceland, after the glaciers melted, had a burst of volcanism. And this is a bit similar here. Where likely due to the decompression, we have this pulse of volcanism, rather explosive in places, but also bringing up very deep material. And here's one of the biggest ones. It's several centimeters across. And this is really bringing cumulate material from very deep. Intriguingly, if you go to some of the other islands, this is 2 rocks from El Hierro. There on the rift zones, we also have these crystal-rich ancamerites. They're just a little fresher. And this is a similar thing. In a companion paper, another PhD student I was co-supervising, Andrea Manconi, he postulated that these things come up from very deep, and he did some numerical models, and he calculated that the decompression translates down to something like 35 kilometers. So we can really tap upper mantle magma storage reservoirs by these large landslides. But on the local economy, a lot of the tourism is based on selling some nice crystal aggregates and things like that, and jewelry made from olivine. And these are actually crystals that dominantly come from very deep. And they are, of course, marketed. So here on the left, there's some mantle nodules. And here on the right is some jewelry that you can buy on the island. And they kind of polish it, and they make necklaces and things like that from it. So I would say that before we go into the Las Cañadas volcano, we should have a short break maybe. I would say give us 5 minutes just to fill up my coffee and stretch my legs.